Okay, and then now we're starting to discuss basically how we can solve a given LP problem. And so far all the examples we have seen basically consist of LP problems with only two variables, right? And remember, so the reason why we looked at LP problems with two variables was the fact that we can draw the feasible region, and then we can graphically basically find the solution, the best feasible solution, if one exists, of course. And then based on that, we were able to classify LP problems into four classes, basically. So an LP problem falls into exactly one of the four cases we said last time. So it can have a single optimal solution, a unique optimal solution. It can have multiple or alternate optimal solutions. It can be unbounded, which means that the objective function can be arbitrarily good, basically, in the feasible region. Or it can be infeasible, in which case there are no feasible solutions. So today we're going to continue our discussion. So I'm going to start with the following question. So let's consider a maximization problem. So suppose that we have an LP problem and the objective function is a maximization version, basically. Okay? And I'm going to start with the following question. So what happens if we add a new constraint to our problem? So essentially, my question is basically in terms of geometry of the feasible region. So what happens if I have an LP problem and I have a certain corresponding feasible region, and now what I'm doing is I'm basically adding a new constraint, and the question is what kind of changes should I expect? So just as an example, suppose that this is my feasible region. Okay, so let's say this is my first constraint, and maybe this is my second constraint. And maybe somewhere over here is my third constraint. And then let's say we have non-negativity. And it's not too hard to see that in this case the feasible region will be given by everything in this shaded area, basically. So suppose that this is my current feasible region. Okay, so I have three constraints and then two non-negativity constraints, so that which gives rise to this particular feasible region. And now my question is the following. So geometrically, what happens if I add a new constraint to this problem? Yes?
There are three possibilities.
Okay.
One makes an inconsistent system.
Okay, that's good.
One creates a feasible region part. And the other is makes no sense.
Well, makes no difference. Okay, that's yes. There's a difference between makes no sense and makes no difference. So, so you're absolutely right. There are three possibilities, basically. Okay, so the first one is that if the new constraint is something like this one, for instance, okay, then what's the effect of this constraint? Well, this new constraint has no effect at all, basically, right? I still have the same feasible region. Okay, so this is the first situation. The second possibility is something like this. So what if the new constraint is something like this? What's the effect of that change? Well, now the new feasible region is actually given by a smaller area, right? So some solutions which were feasible before I added that constraint are not feasible for the new problem, in some sense, right? So this is kind of like saying, for example, if you recall the example of buying a car that I mentioned last time, so suppose that you're trying to buy a car, but you're not willing to pay more than 30,000, for instance. Okay, that already gives you a constraint. And then if you say that, well, I also want, let's say, air conditioning in my car, that puts another constraint to your problem. So that makes your feasible region smaller in some sense, right? So intuitively, basically, every time you add a new constraint, your feasible region cannot get larger, right? And it makes perfect sense because basically constraint means that you're putting another restriction on your problem, okay? So the new red constraint actually becomes an extra sort of restriction. So as a result, this is a second possibility. And the third one is the following. So, for example, if the new constraint is something like this one, then what do I have? Well, now the new feasible region is the empty set, basically, right? So now there are no feasible solutions for the new problem. So as a result, as your friend correctly stated, there are three cases. So the first one is that if you look at the very first line that I draw, it makes no change at all on the feasible region. The second one is it actually makes the feasible region smaller. And the third one actually also makes the feasible region smaller, but to the point that there is no feasible region in some sense, okay? So as a result, we always say the following relationship. So this implies that the new feasible region is always a subset of the old feasible region. Okay? And note that this is true for all cases. So even in the last case, the new feasible region becomes the empty set, but the empty set is the subset of every set, basically, right? So this is a well-defined relationship. So as a result, by adding more constraints, we cannot make the feasible region larger. So that should make perfect sense, okay? So every time you add a new constraint, your feasible region can only get smaller. Either stays the same or it should get smaller, basically. All right, now let me ask you a different question. So again, I assume that this is a maximization problem. What can I say about the new optimal value? So after adding the red constraint, what can I say about the new optimal value in comparison with the previous optimal value? Yes? The best feasible solution may change. Okay. In what direction can it change? Okay. So first of all, let me just clarify one thing. So I'm asking about the optimal value. Okay, so what does the optimal value mean? So optimal value is the objective function value of the best feasible solution, basically, right? So I'm just talking about the real number, whatever that number is. And my question is basically, how can I compare the new optimal value with the previous one? So what kind of a comparison can I write? The objective function value cannot increase, basically, right? So why not? Because, well, if I'm making my feasible region smaller, okay, so that means that there's no way I can find an even better feasible solution than I did in the first case, okay? So in other words, for example, I'm looking for the highest mountain in Turkey, okay? And now I'm saying that, of course, the highest mountain in Turkey is in Ağrı, right? Okay? And then I'm saying that, well, okay, so I'm only interested in mountains in Ankara, for instance, okay? Well, the highest mountain in Ankara cannot be higher than the highest mountain in Turkey, right? Okay? So it's essentially the same idea. So every time you add a new constraint to a maximization problem, your optimal value cannot increase, basically. Okay? You cannot actually get a better optimal value. So as a result, we can write down the following relationship. So the new optimal value should be always less than or equal to the old optimal value. Okay? Now let me ask you a different question. So can we ever have equality, for example? So how can we have equality?
For example, the upper down of the curve. So we can increase our feasible region, but still our optimum value will be same.
Okay, that's good. Basically, think of the following example. Again, suppose that you're looking for the highest mountain in Turkey. Okay? And now instead of looking at the highest mountain in Turkey, you're looking at the highest mountain in Ağrı, for instance. Okay? Those two are the same, basically, right? So as a result, sort of, depending on the constraints, by adding a new constraint, your optimal solution either stays the same, okay? For example, suppose that my objective function actually increases in this direction, okay? So this is my isoprofit line, and this is the improving direction. So what's the optimal value? Well, the optimal value, let's say, will be this one, okay? So the optimal solution, rather. Okay? Now, for example, if I add this constraint, okay, then I still have the same optimal value, basically, right? Because my feasible region did not change in that case, okay? However, if I add this constraint right here, okay, now the best I can do is I can go only up to this point right here, okay? So this is my new optimal solution. Now, here's a crucial observation. So my new optimal solution was already a feasible solution for the first problem, okay? So as a result, my previous optimal solution should be at least as good as this one, basically, right? Why is that? Because in my previous problem, I already considered this solution as an alternative, okay? So as a result, by adding a new constraint, I cannot actually have a better optimal value, okay? I can only make it worse, okay? And depending on whether actually your optimal solution is still feasible for the new constraint, you either have the same optimal solution or your optimal solution will change, will move to some other point, okay? So as a result, for a maximization problem, whenever you add a new constraint, your feasible region cannot get larger. And likewise, your optimal value cannot get larger either. Okay, does this make sense? All right, so let me ask you a different question then. What if it were a minimization problem? So would any of these relations change? So my question is, instead of having a maximization problem, suppose that we have a minimization problem now. So would we still have the same relations between the old feasible region and the new feasible region and the old optimal value and the new optimal value? Well, first of all, think of the following way. So the feasible region, as I said over and over, has nothing to do with the objective function, right? Okay. So as a result, for a minimization problem, we still have the exact same relationship between the two feasible regions. Because whenever we draw the feasible region, the objective function does not have any role, basically, right? Everybody remembers that, right? Okay. Now, whenever we have a minimization problem, let's think about the optimal values. So my objective function value can only get worse, basically, right? Okay. If I put more restrictions, then that can only give me a worse objective function value. So what does worse mean for a minimization problem? So worse means larger, basically, right? Okay. So what's the correct relationship in terms of the optimal value for a minimization problem then? So the new optimal value will be at least as large as the old optimal value. So this is the case for a minimization problem. And if you think about this a little bit, this also makes sense. For example, the deepest lake in Ankara, for instance, okay, cannot be deeper than deepest lake in Turkey. Okay, so it's essentially the same idea. Okay, if you put more constraints to your problem, then you can only make your objective function value worse. You cannot improve it. Okay, and worse basically means larger for a minimization problem, and worse means smaller for a maximization problem. Okay, so it makes actually perfect sense. If you put more constraints to your problem, if you sort of narrow down your feasible solutions, then you cannot have better objective function values. So that's as simple as that, right? Okay? Any questions about this? All right, then let me ask you a different question. So what happens if we remove an existing constraint? So now, instead of adding a new constraint, suppose that I have a bunch of constraints, and now I'm actually removing one of them. So what kind of changes should I expect? Exactly. So now you just expect the opposite, basically, right? So if you remove an existing constraint, that means that you're removing one of the restrictions from your problem, okay? And if you remove one of the restrictions from your problem, then you can only increase your feasible region, basically, right? So in this case, we have the opposite relationship. So this implies that the new feasible region now actually is a superset of the old feasible region. So it actually includes the old feasible region. Can we have equality? So what would be an example?
If we remove a constraint which makes no change.
Exactly. I mean, it's just you should just make the opposite argument. So for example, this red constraint was part of my problem, okay? And if I remove this constraint, then my feasible region stays the same, basically, right? Okay. On the other hand, let's say if this constraint was part of my problem, if I remove it, now I'm obtaining a larger feasible region, basically, right? Okay. So as a result, we have now just the opposite relationship. And again, this makes perfect sense. So if you remove one of the restrictions, then you can only increase your feasible solutions, basically, right? Okay. You cannot decrease them. So what's the corresponding relation between the optimal values? So what can I say about the new optimal value? For a maximization problem again. So now it's going to be again greater than or equal to the old optimal value. So this is for a maximization problem. And what is the corresponding relationship for a minimization problem? So the new optimal value will be less than or equal to the old optimal value for a minimization problem. So basically what this tells you is the following. So if I remove an existing constraint, then I can only improve my objective function value, okay? So I cannot make it worse. And improving basically means larger for a maximization problem and smaller for a minimization problem. Okay? Any questions so far? So these are simple relations, but I think it's also important to sort of know about these relations. So one way to think about an LP problem is that when you draw the feasible region, basically, okay, as we did in the first 5 examples, so each constraint actually makes your feasible region smaller in some sense, okay, or cannot make it larger, more precisely. So as a result, if you add one more constraint, you can only make your feasible region smaller, or it can stay the same. And if you remove an existing constraint, then you can only enlarge your feasible region, or it stays the same, okay? And correspondingly, the optimal value will either improve or will get worse, depending on what you did, okay? All right, so maybe I forgot to mention this last time, but there's one thing that you should also remember. From a mathematical point of view, okay, actually there's no difference between a minimization and a maximization problem. Why is that? So suppose that this is a maximization problem, and this is my improving direction C, okay? So as a result, if I go in this direction, in the old feasible region, this would be my optimal solution, right? Okay? However, I can also view this as a minimization problem, okay? If I simply change the direction of C in the other direction, right? If I just flip the sign of C, basically, and if I view it as a minimization problem, then this would still be my improving direction, basically, right? Okay? So essentially what I'm saying is the following. So if you have a maximization problem, okay, you can multiply your objective function value, your objective function by -1, and you can turn it into a minimization problem, and you would get exactly the same problem, basically. Okay? Why is that? So for instance, suppose that for this problem, my objective function is something like maximize x1 plus x2. Okay, subject to these constraints, whatever the constraints are. So then my improving direction C would be 1, 1, right? So the coefficient of x1, x2. So as a result, it tells me that I should move in this direction. And if I keep moving in this direction, this would be my best solution. So suppose that now I'm going to multiply the objective function value by -1. So I'm going to turn it into minus x1 minus x2. Okay? And instead of maximizing it, I'm going to minimize it. Okay? Well, so what's my improving direction for this problem? Well, first of all, my C would be -1, -1. Okay? But for a minimization problem, the improving direction is the opposite of C, right? Negation of C. And if I multiply this by -1 again, I'll get 1, 1, which is exactly the same as this one. So maximizing an objective function is essentially the same as minimizing the negative of the objective function. Okay? So as a result, again, from a mathematical point of view, there's no difference actually in minimization and maximization. The only difference is that you just have to be careful about the improving direction. Okay? So in other words, you can turn every minimization problem into a maximization problem and every maximization problem into a minimization problem. Okay? By simply negating your objective function. So as I said, you can always, for example, from now on pretend that all the LP problems are minimization problems, for instance. Okay? Does that make sense? So as a result, as I said, again, mathematically speaking, maximization of a function is equivalent to minimization of the negation of that function, and vice versa. Okay? Any questions? All right. So in the first 5 examples that we have seen, we talked about these corner point solutions, and we said that they're kind of important. And every time there was an optimal solution, there was always a corner point which was also optimal, right? So even in the presence of alternate solutions. So now we're going to try to sort of get more insight about these corner points. So first of all, let me give you a formal definition. So def stands for definition. A corner point of the feasible region of an LP problem is a feasible solution that is not the midpoint of 2 other feasible solutions. So I'm going to try to explain what I mean. So first of all, I mean, if you sort of look at this definition carefully, what does it say? So a corner point, first of all, should be a feasible solution, right? So that's important. But it's not an arbitrary feasible solution. It's a feasible solution with a certain property. What's the property? The property is that it shouldn't be the midpoint of 2 other feasible solutions. So what does that mean? So suppose that, again, we still have, let's say, 2 variables, x1 and x2. And then I have my constraint. So this is my first constraint. Maybe this is my second constraint. And let's say this is my third constraint. And then we have non-negativity of x1 and x2. So in this case, my feasible region will be everything in this area. So we can try to identify the corner points, okay, of this feasible region. So essentially, what we do is the following. For example, pick any feasible solution, such as, let's say, this one right here. Okay? So obviously, this is a feasible solution. It satisfies all of the constraints. Okay? So the question is this a corner point or not? Well, what you do is the following. So can I find 2 other feasible solutions? For example, this one and this one, so that my point lies exactly in between these 2 points, okay? These 2 feasible solutions. And in this case, the answer is yes, right? So, for example, for this solution, I can find 2 other feasible solutions, okay? Such that this solution is exactly the middle of these 2. Does everybody see that? Okay? So since this does not satisfy this property, then this point cannot be a corner point, okay? So in other words, if you give me a feasible solution, and if I can find 2 other feasible solutions such that my feasible solution is exactly in the middle of these 2, then it cannot be a feasible, it cannot be a corner point. Okay? What about a point such as this one? Would that be a corner point? Why not? Exactly. So once again, I can find a point such as this one and a point such as this one right here. And again, this point will be exactly the middle of these 2 points, right? Okay? So once again, this is not a corner point. And this is not a corner point either. What about this point right here? Well, so if I want to write this as the midpoint of 2 different solutions, okay? So for example, if I pick a point such as this one, okay, then the other point should be somewhere over here, basically, right? But the problem is that this point obviously is not a feasible solution, okay? So similarly, if I pick my first point to be this one, then the second point should be somewhere over here. Again, I'm going to violate feasibility. Okay, I'm going to violate at least one of the feasible solutions. So unlike these 2 points, this point right here cannot be written as the midpoint of two other feasible solutions. Does everybody see that? Okay, so as a result, this would be an example of a midpoint, of a corner point, sorry. Okay? So there's no way I can write this as the midpoint of two other feasible solutions. So as a result, this solution satisfies this definition. And since it satisfies this definition, it's called a corner point for this problem. Okay? Are there any other corner points for this problem? Well, by the same reasoning, this would be a corner point as well. Similarly, this would be a corner point as well. This would be a corner point as well. And this would be a corner point as well, right? So as a result, for this small problem, there are actually 5 corner points. Okay? And as the name suggests, corner points are corner points, basically, right? Okay? Are points that lie on the corner of the feasible region. So in this case, as I said, there are 5 corner points. So later on, we're going to actually sort of give a more formal argument. But the nice thing about corner points is that there are always a finite number of them. Okay? So that's important. So we know that in general there are infinitely many feasible solutions, but there's only 5 corner points. Okay? So that's important. And that's going to actually sort of allow us to develop algorithms for linear programming. Okay? So in particular, I'm going to tell you this later on, but essentially we're going to show that it actually suffices to look at only these 5 corner points to find the optimal solution. Okay? If there's an optimal solution, of course. So corner points are special, and this would be the definition. Any questions about the definition or the example? Does everybody understand the definition? So basically, you shouldn't be able to write it as the midpoint of two other solutions, okay? So you shouldn't be able to, so that's important. If you can, then that's not a corner point. Okay? All right, so how do we obtain corner points? Well, in LP problems with 2 decision variables, such as x1, x2, such as the ones we have seen so far, a corner point lies at the intersection of 2 lines. Lies at the intersection of 2 lines. So it's not too hard to see that, for example, this corner point lies on this line and this line. This corner point lies on this line and this line. This corner point lies on this line and this line, and so on and so forth. Okay? And we did this when we're looking at the examples. So when we're trying to compute the optimal solution, we just solved the equations corresponding to these 2 lines. So we solved them simultaneously, and we found the coordinates, and the coordinates actually gave us the optimal solution, right? Okay? So now what we're going to do is we're going to try to sort of think about problems with, let's say, 3 variables. Okay, so we haven't seen such an example so far. So let me continue this first. So each corner point in an LP problem with 2 variables, with 2 decision variables, can be computed by solving a system of equations with 2 variables and 2 unknowns. Sorry, with 2 variables and 2 equations, that's what I meant. So with 2 unknowns, 2 equations and 2 unknowns. And that's exactly what we did when we were looking at the examples. So we just looked at the equation corresponding to the first line, we looked at the equation corresponding to the second line, and we solved them simultaneously. And the solution gave us exactly this point right here, right? So the coordinates of this point. Now let me ask you a question. So for example, suppose that in that problem there are 5 constraints basically, right? So 5 constraints define 5 different half spaces. Okay. I'm also counting x1 greater than or equal to 0, x2 greater than or equal to 0 as a constraint because they are also constraints for my problem. Okay. And we also know that every corner point is given by the intersection of 2 lines, basically, right? Okay. So here's my question, basically. If I have 5 constraints in an LP problem with 2 decision variables, how many corner points can I have at most? So what is the largest number of corner points I can have? So how would you compute this? By looking at these remarks. Well, so what does this remark say? So every corner point is obtained by the intersection of 2 lines, right? So every corner point requires 2 equations, basically, right? In other words, every corner point requires 2 constraints, okay? And I have 5 constraints overall. Sorry? Can it be the same as number of? Well, but I think that's a coincidence. So, for example, if this constraint were such as this one, okay, then I would have only 4 corner points, basically, right? Okay? Exactly. So, I mean, one way to think about this is the following. So, the largest number of corner points you can have is the following. So, I have 5 lines, okay, and every corner point is obtained by the intersection of 2 lines, okay? So, in other words, every pair of lines has the potential to define a corner point, okay? For example, this line and this line actually defines this corner point. This line and this line defines this corner point. Similarly, this one and this one defines this corner point, and so on and so forth. So if I have 5 lines, basically, the question actually boils down to the following. In how many ways can I pick 2 lines out of 5? Okay? And that's an easy high school question, right? So basically, the number of ways you can pick 2 lines out of 5 is given by 5 choose 2, basically, right? 5'in ikilisi. Okay, that's a good question. So basically, now one thing you should be careful about is the following. So for example, if I look at the intersection of this line and this line, they also have an intersection, but the problem is that that point is not feasible for my problem, right? Okay? So similarly, for example, if I look at the intersection of this line and this line, then again, this point is not feasible, okay? So that's the reason I said at most 5 choose 2. Okay, so that's actually an upper bound on the number of corner points you can have. So for this problem, what's 5 choose 2? Well, 5 choose 2 is equal to 10. So that means that you can never have more than 10 corner points in such a problem. Okay, so 10 is the largest you can have. So for every LP problem with 5 constraints and 2 variables, you can never ever have more than 10 corner points. Okay, does everybody see that? Is that clear? So once again, the reason why I say at most is because not every pair of lines actually defines a corner point. Okay? But the largest number you can have is, you have 5 lines, and there are 5 choose 2 ways to choose 2 out of 5. So as a result, 5 choose 2 is, I think, equal to 10, right? So as a result, there are at most 10 different corner points in an LP problem with 5 constraints and 2 variables. Okay? Is that clear? Yes. That's a different question, okay? So that's a different question. So, and that's not the question I'm interested in right now. But essentially, that tells you why there are a finite number of corner points, okay? So, because the largest you can have is equal to 10, okay? If the largest is equal to 10, then that means that every time you have an LP problem with 5 constraints and 2 variables, you should always have a finite number of corner points. Does everybody see that? Is it clear why we can have at most 10? Okay? All right, so now let me ask you a different question. What about LP problems with 3 variables? Okay, we haven't seen them so far. And let me give you an example. So suppose that now I'm adding a 3rd variable. And here are my constraints. So the first constraint is x1 is less than or equal to 1. x2 is less than or equal to 1. and let's say x3 is less than or equal to 1, and I have x1, x2, and x3 are all non-negative. So how many constraints do I have? Well, including non-negativity, I have 6 constraints and 3 variables, right? So once again, let's try to sort of visualize the feasible region for this problem. Okay, so in the previous examples, we always had 2 variables, so we only needed 2 axes, right? So one for x1 and one for x2. So now we're introducing a 3rd variable, so which means that now we need a 3rd direction, basically, right? Okay. So as a result, instead of having a 2-dimensional picture, now we're going to be looking at a 3-dimensional picture. Okay. So this is, again, my x1 axis. This is my x2 axis. And the x3 axis will be pointing towards you, basically, right? Okay. And of course, I mean, typical of illustrating that is, so let's say x3 is something like this one. Now, what did we do for a problem with 2 variables? Well, first of all, we looked at the equality version, right? And then after writing down the equality version, which corresponded to a line in 2 dimensions, then we decided which side should we pick. And that gave us a half space, basically, right? That divided the plane into 2, and then we picked the right side. So we're going to do exactly the same thing here, okay? So what I'm going to do is I'm going to start, first of all, with the equation x1 equals 1, okay? So what kind of a region does x1 equals 1 describe in this picture? So it actually defines a plane, right? Okay, so it actually goes through x1. So essentially what I'm doing is I'm looking at all points whose x1 coordinate is equal to 1. Okay? And if you think about this a little bit, that's going to be basically a plane that goes through this point right here. Okay? Now in 2 dimensions, the equality defined a line. In 3 dimensions, an equality defines a plane, basically. Okay? And if you think about this a little bit, again, the same analogy works. So that plane also divides your space into two portions. Okay? The left side and the right side. Okay? Then you should decide which side should I pick. Well, so you can again try the origin, 0, 0, 0. Does 0, 0, 0 satisfy this inequality? Yes. So as a result, the correct side will be the left side of this plane. Okay? So the only difference is that rather than having a line, now I'm going to start with a plane, basically. Okay? So things are getting a bit more complicated. But essentially, at least at a high level, you have the same picture. Okay? So every constraint divides the plane into 2, divides your space into 2. Then you should decide which side you should pick. And for x1 equals 1, you should actually pick the left side. Okay? What about x2 equals 1? Well, that defines a different plane, right? So what kind of plane does that define? So now it's going to be this plane right here, right? So now I'm going to fix the x2 component equal to 1. So it's going to be a plane which is parallel to the x1, x3 axis, basically, right? Okay? So this is going to be my second equality. Again, I'm going to think about, well, which side should I pick? Well, I should pick the lower side, basically, right? Because, again, if I plug in the origin, 0, 0, 0, it will satisfy this inequality. And finally, what about x3 equals 1? So now I'm fixing the x3 component equal to 1. What kind of a plane do I get? So I get something that's actually parallel to the x1, x2 axis, basically now, right? So if this is my x3 axis, I'm actually fixing the x3 component equal to 1. So now I get a plane which is parallel to the x1, x2 axis. Does everyone see that? Okay. So again, should I pick the front side or back side of this plane? I should pick the back side. So as a result, now I have the left side of this plane, the bottom of this plane, and the back of this plane right here, so far. Then I have non-negativity constraints. x1 is non-negative. What does that mean? Well, x1 is non-negative. x1 is this axis. So once again, think about the plane x1 equals 0. Okay? Well, x1 equals 0 is exactly this plane right here, basically, right? Okay? So that corresponds to this plane, which is parallel to x1 equals 1 plane. Okay? So now I have to be exactly in between these two planes. By the same reasoning, I have x2 equals 1 and x2 non-negative. I should be between these two planes. And by the same reasoning, x3 is non-negative, which is the same as the board, and x3 is equal to 1 is this plane right here, so I should be between these two planes, okay? So what happens if you combine the 3? You get a cube, right? Exactly. So your feasible region will look like this one right here. So now our feasible region is three-dimensional basically, right? So instead of having a two-dimensional picture, now we have a three-dimensional picture, okay? Now that's the only change when you increase the number of variables basically, okay? So in 2 dimensions, you get a two-dimensional feasible region. In 3 dimensions, you get a three-dimensional feasible region. And if you had 4 decision variables, then you would have a 4-dimensional picture, okay? The problem is that I cannot draw that, okay? However, at least conceptually, it's always good to sort of have this picture in mind, okay? So there's always a feasible region. Even though you cannot visualize it, it actually looks something like this one, okay? Either this one or that one. So now let me go back to this example again. Now what are my corner points for this problem? Well, it's going to be the corner of the cube basically, right? The corners of the cube. So how many corners does a cube have? Well, a cube has 8 corner points, so as a result, we now have for this problem a total of 8 corner points. And it's not too hard to see that any other feasible region can be written as the midpoint of 2 other feasible solutions, right? Okay? So in this case, we have 8 corner points. And once again, just like you did it for 2-dimensional LP problems, you can also graphically solve the 3-dimensional LP problems as well, okay? By using exactly the same procedure. So you start with x1 equals x2, sorry, x1 plus x2 plus x3, let's say is equal to 0. That defines a plane now, okay? That defines a plane, which is not easy to draw, so I'm not going to draw it, okay? But the normal vector will be 1, 1, 1, okay? So if you think about these 3 axes, this is going to be my normal vector in some sense, okay? So now my plane will be perpendicular to this vector. And by the same reasoning, I'm going to try to push it in this direction as far as I can, okay? Because it's going to be the improving direction. And what would be the best solution in this case? 1, 1, 1 would be the best solution, exactly, okay? So essentially, I'm going to start from here, okay? And I'm going to push it here until I hit this point right here. So that's the best I can do, okay? And the optimal value for this problem will be equal to 3. Of course, the problem why we don't do 3-dimensional examples is that because it's more complicated to draw in some sense, okay? But the basic idea is exactly the same, okay? So you have an improving direction. You have your isopropyl plane this time. It's not a line, but it's a plane, okay? And you want to move your plane perpendicular to the improving direction as much as you can without leaving the feasible region. And you would get exactly the same, using the same procedure, you would get the optimal value, okay? Now let me ask you a different question. Now, in 2 dimensions, every corner point was given by the intersection of 2 lines, right? So what about in 3 dimensions? So how do we obtain corner points? Well, so first of all, we know that the boundary of each constraint is a plane, right? So think of this as a plane, okay? And think of this as a second plane. So what's the intersection of 2 planes? It's a line, right? So basically, intersection of 2 planes is not enough to get a corner point, okay? So what else do I need? Well, I need one more plane, basically, right? So think of, this is my first plane, this is my second plane, and if I also intersect with the third plane, now this corner is the intersection of 3 planes, basically, right? So in 2 dimensions, we needed 2 lines for a corner point. In 3 dimensions, we need 3 planes, basically, okay, for a corner point. And it's not too hard to see that. For example, if you look at this picture, for example, if you look at this corner point right here, it's given by the intersection of this top plane, this side, and this side as well, okay? So as a result, this is given by the intersection of the plane number 1, plane number 2, and plane number 3, okay? Similarly, this one is given by this plane, and the bottom plane right here, okay? So in 2 dimensions, we needed 2 lines. In 3 dimensions, we need 3 lines. What are 4 dimensions? Well, you would need 4 equations, and so on and so forth, okay? So now let me ask you the same question again. You have 6 constraints here, right? And you have 3 decision variables. What is the largest number of corner points you can have? So now, for each corner point, you should choose 3 planes. And there are 6 planes. So you can pick at most this much, basically, right? And what 6 choose 3? So it's going to be 20, right? Okay? So as a result, if you have an LP problem with 3 variables and 6 constraints, the largest number of corner points you can have is 20. And 20 is still a finite number, okay? So you cannot have an infinite number of corner points. Question? All right, any questions about this? Yes?
Can we say the optimal solution is one of those corner points?
Yes, we can and we will, okay? Because by the same reasoning, as I said, you know, once you find your improving direction, you should actually move in that direction as far as you can, and the last point you hit the feasible region will be an optimal solution, okay? And just like we did for 2-dimensional examples, again in 3 dimensions and in every other dimension basically, it's going to be the case that the corner point will always be an optimal solution. Okay? Other questions? All right, so let me just write down what I said and then we'll take a break. So, so as a result, in 3 dimensions, a corner point is given by the intersection of 3 planes. And once again, hopefully you sort of see a trend here. So in 2 dimensions, we need 2 constraints to define a corner point. In 3 dimensions, we need 3 constraints to define a corner point. And if I have, let's say, 50 dimensions, then I'm going to need 50 constraints to define a corner point. Okay, we're going to see this later on. But there's a one-to-one correspondence between number of variables and number of constraints you need to define a corner point. Okay? Any questions? All right, so let's stop. We'll continue after the break.